cannot be recorded. Welcome all to Adel Bibi's PhD thesis defense. The committee members are myself, Peter Richterik, Wolfgang Heydrich, and our external examiner from Berkeley, Ima. And today, Adel will give a 45-minute, I hope, presentation at max, and then that will be followed with general audience questions, and then after that, the general audience will be asked to remove themselves from the Zoom channel. Otherwise, one of the hosts or co-hosts will remove them. Then there will be questions among the committee and Adel alone, and then Adel will be asked to remove himself from the Zoom. The committee will convene, make a decision, and let Adel know. Okay, so that's the process. Adel, please go ahead. You'll have like 45 minutes from now.
All right, thank you, Bernard. I hope that I can make it in 45 minutes because I was timing myself around 50 minutes, but hopefully that
50 is fine.
Okay, great. So can everyone see my, at least the committee members, can see my screen?
Yes.
Slides. Okay,
Yes.
Great.
Yes.
Thank you, Bernard, for the introduction. This is Adel Bibi, and I'll be talking about what I've been working on during my during my PhD years for the past around 4 years, which almost always around the topic, which is understanding a block of layers, but we're going to do it from 3 different perspectives: an optimization, probabilistic, and tropical geometry perspectives. So to make sure that we are all on the same grounds, deep learning can be seen as a reincarnation of neural networks, and they are simply stack of some mathematical functions. And they're an excellent tool to understand data. And specifically in the visual domain, it seems to be rather easy for neural networks to perform high-level tasks, things like semantic segmentation, object detection, classification, and these sort of type of tasks, as well as in other domains like reinforcement learning, where they are extremely powerful in learning these type of strategies and policies that can defeat world champions at several games, like complicated games like Dota 2, StarCraft 2, where the action space is very large. In many cases, people usually look at this as a black box, specifically practitioners. And for the most part, this is doing very well. And you don't really have to know much about the mechanistics that happens in the background of this black box. And one way to look at this is simply a regression machine or curve fitting, if you will. And you don't mind a lot what happens, the intricacy levels with what happens in the background. However, there are several issues that keep arising from time to time, and one popular issue is adversarial attacks, in which in many cases networks can look at this panda and classify it correctly, but it seems rather easy to construct this small imperceptible noise, at least to the human eye, in which the network misclassifies this into a gibbon. What is annoying about this behavior specifically is that it's rather easy to construct such examples. In some cases, taking a single iteration step of some loss function with respect to input is sufficient to construct such adversaries. And we want to understand why such behaviors happen, along with any other other nuisances in neural networks. And it's not sufficient to just look at it as a black box. But the problem with coming with generic theoretical reasoning for their behavior, there are many difficulties and challenges, generally speaking, but also neural networks come in all shapes and sizes. And it's very hard to come up with answers under all these different variations from fully connected convolution layers, different activations, rest connections, dense connections, and all that. So instead of for this thesis, what we're going to do is take a bottom-up approach in which we are going to look at one specific block that is shared among multiple architectures. And this block, for the most part, for some part of this presentation, will be a dropout layer followed by an affine transformation, followed by another, followed by nonlinearity. And we want to look at this for as much as we can for the most general case where nonlinearities could be anything. The affine transformation can be also anything, fully connected or convolutional, and different types of dropouts. And as I mentioned at the beginning, we're going to look at this from 3 different perspectives. optimization, probabilistic, and tropical geometric perspective. So I'll start with the optimization perspective. And here what we're interested in really is not training the network as much as saying the network is pre-trained. And we want to ask questions about the activation output of these layers. Is it possible that these activations are special from an optimization perspective in some sense? That is it possible they are actually solutions to some KKT problem, for instance? And to handle this, there is really this dichotomy in the literature where everyone, whenever they try to analyze such a thing or similar questions, they really stumble upon this issue with affine transformations, in which they develop the theory for generic unstructured matrices, fully connected layers. And when they want to generalize it to convolution layers, they refer to saying that, well, convolutions are linear operators, they can't be parameterized with some matrix, and they ignore somehow the structure because it's rather not very intuitive to get, let alone asking some more difficult questions like diagonalizing such operator. And we want to, at the beginning of this journey really, of this optimization perspective, is try to come up with a way to handle this in a more abstract way where we can get non-trivial results out of it. So we'll take two journeys. Some of them are far away from deep learning, in which we will be asking questions about the lasso problem specifically, where we want to ask whether or not, since we're looking at this from an optimization perspective, is if we go to classical problems, something like lasso, is it possible to transform this into convolution-only operations, 1D convolution-only operations? And we'll see how such reformulation can be actually heavily related to a problem well known in the vision community as convolutional sparse coding. And then we'll merge the pieces together to actually come up with a general understanding to these convolutional layers and answer these optimization perspective questions. So let's get started with the optimization perspective, which is the FFT lasso. So as many of you know, that the lasso has seen lots of applications, but since I come from computer vision background, face recognition is specifically one of the most popular applications for such a problem in the vision community, in which we would like to solve such a problem for a very fat dictionary A, where you have blocks of matrices that represent faces of different people. And the assumption here is that the frontal faces under different lighting conditions more or less lie in the same low dimensional subspace, in which once you solve this for some query image B, the density in C will tell you something about what classes this belong to. Now we're interested in solving this, perhaps reformulations to it too, in which we're interested specifically in first order deterministic solvers, solvers like proximal gradient methods or ADMMs and so on. And one very popular solver to this, of course, there are many that exist there for such a problem, heavily studied problem, is applying ADMM to the dual of this problem. And the reason behind this is basically you have this dimensionality flip in terms of the number of variables. And really the bottleneck of solving such an algorithm with ADMM is actually having to solve a linear system iteratively. And in the dual domain, this would be of size m by m. These matrices are generally fat, in which you really can only solve this in a smaller linear systems. What we really want to do is to have some algorithm, something similar to that, perhaps to ADMM, but maybe can enjoy the same properties as ADMM, but perhaps can have a lower computational complexity, or it allows for something like trivial parallelism over GPUs. And to do so, what we do is essentially we do something at the beginning that's somewhat counterintuitive, in which you say, okay, this is my problem. And what we're going to do is I'm going to lift this problem to some higher dimension. And the way I'm going to do it is essentially take each column of this big fat dictionary A and generate a circulant block out of it by running several permutations of this first column. And in order to make sure that the both problems are actually equivalent, what we're going to do is to enforce those sparse codes that are interacting with the synthetic columns that we have appended to be exactly zero. That's just simply another linear equality constraints. And I'm claiming here, perhaps it is much easier or better, perhaps, to solve this lifted problem, which is larger in dimension, and it's now even constrained in solving the original problem. So let's see why is that potentially could be the case. So this is the lifted problem that we have. And because A tilde is blockwise circulant, what turns out to be is that this is basically performing convolutions with blocks of the sparse codes themselves. And when you look at this, this looks like an inference step of dictionary learning problems, but specifically convolutional sparse coding problem, but it's now constrained. And this seems like it's very heavily related to such a problem, which is something we'll touch upon later on during this presentation. So, but what is this linear equality constraint are actually doing? Well, essentially they are enforcing all none, except for the first element to be zeros. And essentially we're forcing these sparse codes to belong to a set of Dirac delta functions. And we know that the convolutions with that is essentially just scaling these columns. And this basically recovers the same exact problem. But what I want to highlight here is that we started with a problem with very unstructured matrix A, which you can think about it as a fully connected operation in neural networks for now. And we can, there's somehow an equivalency where you can lift this to a higher dimensional problem where the matrix A is now very well structured, but the operations are now all done in a convolutional way. So what is exactly FFT lasso so that we are proposing? Well, essentially it is applying ADMM to the dual of the lifted problem. So this is my original problem. I'll lift it and then generate a dual out of this for the same reason for why would you apply dual ADMM to lassos for the same exact reason. But what does this gain us exactly? Well, because of the structure and we're doing convolution, so now we can think about updating these variables, running the same algorithm, but actually having all these variables to be updated in the Fourier domain. So what you can observe that the linear system now is separable in coordinates and it can be solved exactly by simply doing element-wise operations of those transforms. And the most really expensive operation in all the updates is actually computing those fast Fourier transforms, which can be very efficient. We do one extra step in FFT lasso where in the dual variables, we do something like a Nesterov-like update to them. But aside from that, there is really nothing that's heavily computation expensive beyond computing those fast Fourier transforms. So the complexity looks something more or less like this. I have n columns and I need to take Fourier transform of those. The Fourier transform of each one of them would be, each one of those would be of size m. So that's a complexity m and n log m compared to the worst case complexity of solving that linear system, which is n cubic. So this really fits the paradigm when I have dictionaries of large dimensions in both the number of rows and columns, but I don't necessarily have significantly more columns than I have number of rows. So with this, we conduct lots of experiments around CPUs and GPUs, and you see how this can be trivially parallelized because everything is element-wise. We only need to aggregate set of vectors and then communicate them back again in one of these updates. And you can get, due to this hardware acceleration, a significant speed-ups as the dictionaries go larger. Now, another thing that is very nice about this is that if you had dictionaries that are very large in both dimensions, that you can't even fit it into a single RAM, for instance, but you still want to solve this on GPUs. What you can do in this case is, as you would know, is that we can simply actually split this into arbitrary number of vertical splits, because really the only thing that we need to compute is the fast Fourier transform of these columns. And we need then to aggregate them together and communicate them. So this is trivial. But even if it was large in the number of rows, in fact, we can also split it vertically because we know precisely how to relate the fast Fourier transforms of long vectors with respect to the fast Fourier transform of individual pieces by shifting them by some complex exponentials. So this allows, this new formulation allows for trivial hardware acceleration. We can take this, let's say, million by million dictionary and split it arbitrarily, horizontally and vertically into far more GPUs and run the same algorithm very easily. Now we also measure such an algorithm on, instead of monitoring the loss function, you can also monitor it through the behavior in terms of accuracy and how good it does when it does on classification task on face recognition data sets. And it also competes very well with dual IDM. Right, so what do we see from here? What we really see is that fully connected operations or unstructured matrix vector multiply can somehow equivalent in high dimensions to performing 1D convolutions. And we've seen that this problem is very much related to convolution sparse coding. So this seems to be the natural next direction to go and to see how these problems relate to each other before answering the big question of how to unify those two pieces together. So what is convolutional sparse coding? Well, it's essentially dictionary alignment problem. The only difference, the major difference, is that the sparse codes and the dictionaries are interacting in a convolutional way. And what you hope to do is to solve this for a large number of dictionaries D, in which they are representative enough where you can use them to reconstruct any new natural images. And now one challenge at the time with such problems is usually the images, or the data that you want to reconstruct are two-dimensional. So these Ys, the images, or the dictionaries D, the sparse codes are usually two-dimensional. So if you had something like RGB images and you want to reconstruct those, one way to do it is basically reconstructing each channel separately. But unfortunately, this actually loses some information about the correlation between the features themselves. So what we really want to do now is we want to generalize this to higher order dimensions where the data could be represented in an arbitrary order tensor. So to alleviate this, we refer to the multilinear algebra literature. And specifically, we look at a specific type of tensor product called tensor SVD. And this works only for third order tensors. And the order of the tensor is the number of indices you need to slice that tensor. And it goes as follows, saying that if I have two third order tensors, A and B, you can carry out this product by, this is how the definition goes. You unfold that tensor into a matrix that's very well structured, in which you have those frontal slices stacked as a set of columns, and then you circularly shift these blocks together. And then you do the same thing for B, without the circular structure. You carry out a matrix vector multiply. And once you're done, you fold it back again into a third order tensor. Now, this has lots of applications, and one nice thing about this particular type of unfold is that this can be blockwise diagonalized with the tensor product between a discrete Fourier transform, normalized discrete Fourier transform, and identity matrix. And along the blocks, essentially you have those frontal faces of A, but after taking 1D Fourier transform along the last dimension. And what we want to do is to extend this to arbitrary order tensors, and we want to see what is the right unfold of that tensor that presents to us a very nice diagonalization properties that we can use to generalize to arbitrary, to convolutional sparse coding. So I'll show you the machinery, and I'll leave the result after this machinery. So this is how the unfold would look like. Is if I have a fourth order tensor, in this example, N1, N2, N3, and 4, this is how the right unfolding should look like for us to be able to do something useful for such an operation. You start with one of these last dimensions, either N3 or N4, sorry about that. And for example, with N3, and you unfold that along N3, and then you apply the circular shift. So this column here is the same as that, and then you circularly shift these blocks together. Now, since we did this along the rows and columns, now this is a tensor matrix that's of size N1, N3, N2, N3, and then N4. And then I repeat the same thing exactly, but unfolding along this last dimension N4. I'll block it, so you have these green blocks here, and then I circularly shift these blocks. What is interesting about this unfold, so you can apply this recursively for arbitrary order tensors. Now, what is nice about this is that you can show that this has very nice properties in which it can be blockwise diagonalized by taking your tensor, taking 2D Fourier transforms along the last two dimensions, and then stacking those frontal faces along the diagonal. And surprise, surprise, you can show that such a well-structured matrix can be blockwise diagonalized by the tensor product of normalized discrete Fourier transforms and identity matrix. That's great. Now, what we can do is we can refer back to our CSC problem, let our data to be arbitrary order tensor, Y, with arbitrary number of channels, and carry out these convolutions through this operation. But in order to understand exactly what this is doing, I want to show to you first that this reduces many standard operations that we know in the literature. For instance, if I set the dimensions right, in which the first two dimensions are 1 and 1, I only have two dimensions, N3 and N4. If I carry out this precise unfold, I will note that it can be blockwise diagonalized with a tensor product of two discrete Fourier, normalized discrete Fourier transforms. And if you actually unfold this, the structure you get is precisely this PCCB matrix, which is the 2D convolutional operator, which is well known as block circle into circle blocks. Meaning that this operator reduces to performing 2D convolutions, recovering back again the standard CSC type of formulation. In addition, if I had this tensor to be a 2D matrix, well, that unfold basically, so I only have the 2 dimensions, I don't have those in 3 and 4 onwards, that unfold will be an identity matrix, and this can be blockwise diagonalized with a matrix of size 1 by 1. That means this is actually a matrix vector multiply. And this operation, therefore, depending on the dimension of data, recovers standard dictionary learning problems or standard convolutional sparse coding problem. So this is what we want to do. And the question, how would we solve it? Well, there is nothing really fancy about this because we know that this is just another linear operator. But because it can be blockwise diagonalized with tensor products of orthogonal matrices, therefore, the tensor product of orthogonal matrices is orthogonal by itself. And therefore, this is preserved under L2 norm. And thus, we can use similar tricks used in the literature. And since the problem is biconvex in nature, we can alternate between sparse codes and dictionaries over convex problems where we're updating the variables in the Fourier domain completely. Now, we still need to invert linear systems because remember, we have these, along the diagonals, we have dense block cyclic matrices. The same thing can be applied again to the dictionary elements where the same trick can be applied updating these dictionaries. Now we have to ask, okay, how well does this work if I want to use such a method to reconstruct RGB images, for instance? So there are standard data sets for this where we can test this. And really the bottleneck and the major result that I want to pinpoint here is that TCSC here is using our method. So T for tensor, CSC is convolutional sparse coding. And SCCSC essentially is reconstructing these channels independently. So doing 2D convolutions for each one of these channels separately. And what you would observe is that you have, of course, this is a high DP rate, but the dictionaries are still much better because we're looking at these correlations among the data. But not only that, but if you take the dictionaries learned through this joint operator and use them to reconstruct each channel separately, if you do that, this is what you get. It's still even better than using the dictionaries learned on each channel separately. And the reasons behind this is that the parameters here are much smaller than constructing it for every channel separately. And the reason is because we have those sparse codes to be shared across the features themselves, in which this allows us for more generalization capacity in the dictionary learnings. Moreover, you can do lots of other applications, for example, colored video reconstruction, where you're interested in constructing full frames. So we train on those red images, and then we try to reconstruct missing intermediate frames, and we can do there very successfully. So if you think about this, this is RGB image, so this is third order tensor, but I have a bunch of frames that I want to train on, so this is fourth order tensor. But then I have a set of filters, therefore my dictionary is actually a 6D tensor. And such an application can be trivially extended if I want to learn from a set of videos and reconstruct a new video altogether. So great. So now what we have seen is something that somehow there is a relation between convolutions and fully structured convolutions and unstructured matrix vector multiply. But how does really this answer our main question of this unification in order to be able to answer these questions about the properties about these activation functions? Well, we'll go back to our framework back again. So I'm interested in this block of layers specifically. Let me tell you do a small detour in which what do people usually do, at least in the vision community. A student would come in and would say, okay, I want to solve one of these problems, denoising and painting one of these problems. You have one of two approaches. Either go through the classical approach where you formulate this and throw all the information we know from signal processing information theory into this prior function G, solve this and hope we do very good. Up until a certain point, now what you can even do better is train this massive network, collect lots of data, train massive network and ignore this information. You can do even better with it. But there is something better than both of them, which is a combination of both, in which what you can do is say, okay, why do we throw all this information about this function that models the problem very well? What we can do is say, okay, since this models the problem very well, let me select a solver that solves it. And now running this solver for n iteration is equivalent to running somehow each iteration represents a block of complicated layers or structured layers And then we basically apply this block over and over again. So the parameters from 1 to n are actually shared through the algorithm, and we're getting intermediate representation, intermediate solutions to this algorithm. So what is even better you can do is actually to keep the structure coming out from the knowledge we know, and let each one of these blocks be learned in a data-driven approach. So the structure comes from the modeling part, and the free parameters from the algorithm that you're using comes from a data-driven approach. And this has shown to be outperforming most of the existing literature out there. So, but the problem is that all of this is actually one direction. You say, I want to solve that problem. This is the objective function that works very well. Let us construct structured layers that actually gives us a neural network that can perform better on that objective. But what we want to do is go through the other way around. We say that if I'm given a neural network that performs very well on a specific task, I am interested in figuring out whether or not these activations, these intermediate activations, are solving some objective functions, underlying objective function. So far we don't know what it is or how are we going to use it for something useful. So I will start with a small motivational insight. Well, let's look at a very simple example. So we'll start with a fully connected layer followed by some nonlinearity. And we'll assume that those parameters are fixed. So I'm doing a forward pass through this layer. The output activation would look something like this. So this is 0 is my nonlinearity. Now what I'm going to say is something not natural, which is I'm saying, let's put down an objective where the variables that I'm optimizing for are actually the output activations. So the parameters of the network are all fixed, which is I'm not doing training anymore. And if this f is quadratic, and we want to run something like proximal gradient method with optimal step size and all that, this is what the update would look like. So the input to this algorithm would be the previous activation and the parameters of the network. And when we do such a thing, if I did something silly, which is basically do this for a single iteration and make the choice of silly step size of L equals to 1, the update for this algorithm for a single iteration looks something like this, which looks awfully similar to doing a forward pass through a neural network. Now, in order to convince you that this is actually interesting, I want to show to you first that you can prove the existence of lots of prior functions G such that the proximal operators are well-known nonlinearities in the literature. So we can show the following results, where you say, if my prior assumption on the output activation functions were non-negativity assumption, for instance, this gives rise to this real function, for instance. Now, there are others that are non-intuitive, but also very interesting. For example, if you put down prior functions in a log barrier type of way, the proximal of those will recover very, very nicely in approximated way the soft loss 10H. But also, if you have these squared SVM type loss, you get the generalized TKB law. And it's generalized because you can control the shift of the function along with its own slope for the negative term. So what do we have now? Really, all I talked about is this having fully connected, and this nonlinearity is captured by this prior on the output activations. And we want to generalize and abstract this to beyond fully connected layers to include convolutions and to understand what the dropout do into all of this line of work. Great, so why are convolutions really not trivial when we want to ask questions about their diagonalization, for instance? It's because we fully understand how we can diagonalize the 2D convolutions by essentially we're doing 2D convolutions across the activation maps. And then the problem is that we have to aggregate those together. And this type of operation is not easy to work around with. And the issue is that when we have multiple filters, we'll have multiple activations. So how would we deal things? So things like, what is the underlying structure out of this operation? How would we diagonalize such a linear operator? Or at least blockwise diagonalize it? Well, the answer to this comes into this following lemma. And let me parse it for you for a moment. So if I have a set of bank of filters, so I have N2 filters, and I have N1 channels, and the spatial dimensions are W and H. The previous activations were W and H as well, with N1 featured representations. Now, it turns out that this operator that we proposed before for convolutional sparse coding recovers precisely this convolution operator. And because of this, and actually this is not just, we know lots of properties about this, like blockwise diagonalizing this as well. So it turns out that the right objective that we should be minimizing to recover the standard, this one single iteration notion, is precisely that. So we cover, again, this is still quadratic, right? Because this is still multilinear, or if you will, linear operator. And for generic G over this tensor random variables, over this tensor variables. And then you say, okay, I would like to optimize this, but maybe perhaps I want to also optimize it good, in which I want to come up with a way to compute the optimal step size, constant step size of this Lipschitz gradient of this function. And to do so, we show the following result. And specifically because we know how to blockwise diagonalize such an operator, we can come up with a result for such a thing, where it is the maximum across a set of eigenvalues, where the eigenvalues are basically, as you would expect, you'll take 2D Fourier transforms along those spatial dimensions where you're doing convolutions, and then computing SVDs for many number of matrices, but they're all small size, so they can actually parallelize this. And this work was accepted and submitted to ICLR 19. And to our surprise, the same year, there was a paper by Google Brain titled The Singular Values of Convolution Layers, in which they derived precisely exactly the same result. Now, at the time, we didn't know really that we could use this result to diagnose convolutional operators, but it was very exciting to us to know that we derived the same exact result in completely different 2D approaches. So you can immediately see that the diagonalization for an operator is actually a superset over n squared, where n squared here is w times h. The assumption here there is that they are all, both are equal. Right, so what is really the big picture here? Or how does, dropout play a role in all of this? Well, dropout introduces stochasticity into the Fourier path. So the question is it really possible that dropout are linked to solving stochastic algorithms to that specific objective? And the answer, it turns out that it is the case. So for example, if you use Bernoulli dropout, which is your typical dropout that you use, this is somehow equivalent to sampling these functions stochastically with a fixed mini-patch size for a single iteration. Meaning if I run a stochastic proximal gradient method onto this objective for a single iteration with a unit step size, this is equivalent to doing a forward pass through a Bernoulli dropout followed by a generic affine transformation, whether convolutional or fully connected, and followed by another nonlinearity. And also other types of dropout, for example, additive dropout, where you add some noise sample from some distribution. Well, this addition tells you something about maybe we can use variance reduction type of algorithms, where you're adding an unbiased estimator to your gradient to run the algorithm. So what is the big picture really? It seems that we have the right objective in which solving this for a single iteration is equivalent to doing a forward pass through a block of layers, in which the prior term I have on the output activations is controlled. It changes the nature of this nonlinearity that we're having, and the nature of the stochastic or deterministic algorithm I'm using to solve that objective changes the nature of the dropout I'm using. And the question is really if neural networks are performing very well while very crudely approximating such an objective, what would happen if we better solve that problem by running that for several iterations? So we have this feedbackward loop in which now you go to a network, you replace that block with a recurrent solver or with a stochastic optimization algorithm before generating the next activation. So this is what we do. So for the Toyland experiments, if you will, we start with Linette. So DD indicating dropouts. And so you have two blocks of layers, each of them having dropouts. And what we do essentially is we replace those two blocks with the corresponding stochastic equivalent algorithm, and we run that for a few number of iterations. And we notice that there is an improvement in terms of generalization to the behavior of such a network. And specifically now you see that there is a standard deviation here. Now this standard deviation is because the network now is stochastic in inference time, because we're running a stochastic inference to output these activations, intermediate activations. So this is also consistent if we do experiments on an AlexNet on Cypher 10 and Cypher 100. We also do experiments on VGG 16, Cypher 10 and Cypher 100. And really, we don't have theoretical backing for why the generalization behavior improves. Beyond that, we have established this equivalency in which perhaps getting better approximation to that objective function helps us to improve generalization. So if neural networks are performing well under this very crude approximation, maybe getting better solutions can help the generalization. We also conduct experiments to see this relation between dropout and mini-patch. We know that increasing dropout to very high rate will drop the performance, and this is equivalent to decreasing the mini-patch. which is the behavior is consistent in which the behavior drops as you decrease the mini patch or increase the dropout. However, the drop is much graceful for mini patch, and the reason is because you're having those feedback loops in which you have higher chances of sampling more activations. Now, I want to highlight this improvement is not coming from any over parameterization. The same number of parameters are applied, but we're doing extra computation, so we're applying the same operators over and over again. So this is for that optimization perspective, and we can jump into the second part, which is the probabilistic perspective, in which now we're interested in looking at the behavior of the network when it is subjected to some type of noise. And really the ultimate dream for us is that if I have some arbitrary input distribution at the input, one would like to get some analytic expression for the probabilistic density function output of such arbitrary deep network, or maybe just point estimates, mean and variance perhaps. Generally, we already know that this is extremely difficult, even if we choose one of the most stable distributions that we know of, let's say the input is Gaussian. So what we're going to do is follow up the same procedure. We're going to take a bottom-up approach, but we'll take a slightly more realistic block without the dropout, because usually in inference time, we don't have these block-out layers. And we'll look at this affine reload affine. We'll subject it to arbitrary Gaussian noise. I'll ask, can we say something about the output mean and variance? Can we get closed form expressions for those? Now for the mean, really, it's not very difficult. It's rather easy to show such a result. So our function G here is the affine reload affine sort of transformation. And this is what the closed form expression for that looks like. And then the problem comes when you want to compute the variance of such a function. And that's a bit difficult. And what we do is we extend the following result. And what it says basically, if I have any arbitrary nonlinear map, and a very, very mild assumption of this, so this could be as deep as neural network, it relates essentially the expected values of the derivative of this function to the derivatives of the expected value of this function with respect to the covariance matrices. So I'm not saying anything about how difficult or easy to solve this problem, but if it is, if we solve this differential equation, we'll be able to get this expected value. So this psi of x could be now our favorite small function linearly. Now I want to highlight that this is an extension to Robert Price's result that at the time was published in IEEE, in information theory. The extension was that we have no assumptions on the variance, and we have no assumption that the function has to be split coordinate-wise. It does not have to be product of coordinates. So using this result, now we can actually derive the variance expression, or at least the second moment for now. The problem though with this was that it was still really difficult at the time to come up with a closed formula in elementary functions under generic mean distribution. So we had it with respect to zero mean, but we later managed to extend this for arbitrarily Gaussian distribution input, where we have this result, but unfortunately they are too complicated. We have used them for other applications, but I'm not going to emphasize those for now. These functions are not elementary, and we still have to do some approximation for them to solve them, but there exists some nice closed form solutions for them. So from now on, we'll use the variance where we have the assumption of zero mean. So what do we have? I'd like to call this a practically useless network, because it's rarely the case we see such a network for something useful. But we have very powerful tool. We have analytic expressions for the behavior of such a network. Now, since most networks actually don't come in this shape, the question is how useful are these expressions? Well, now what we can say is that if I have arbitrary deep network, how can I transform it into the form that I have? Well, I want to change it into affine reload affine, so I would need the reload somewhere. So what you can do is you can select any reload in the architecture that you wish. Let's say I selected this one, and you just simply linearize the first part of this network into some affine map, and you linearize everything before that into an affine map. And now this closed form expression, this network, we have closed form expressions for the behavior of this moment and variance, which can help us say something about the behavior of the original bigger network, since one is an approximation to the other. Now, I don't want to really bore you about some of the synthetic experiments, but we did lots of experiments to see how accurate is this under linearization, under different architectures, and whether they predict the maximum or not, or experiments. But some nice experiments that you can do as well is to look at that. Since we have expression for the expected logit score at the output of the network, we can actually plot those behavior, because we have this formula as a function of the input variance. So I can see now how the logits interact by just simply plotting this function. Otherwise, you would really have to sample Gaussian distribution at the input from higher dimensional input and then averaging out those estimates and plotting these. But now we can actually just plot these functions and see how does the network actually perform under such distribution. But the more interesting results that you can do is you can do, because we have the average behavior of the network subjected to some noise, we can do sensitivity analysis in which we can say what subset of pixels correspond to the highest corruption at the output. Well, we can just simply evaluate these functions for every one of these classes and evaluate it for covariance matrices that are sparse corresponding to the pixels that we want to corrupt. So if I want to corrupt only the upper part of the image, I'll look at the covariance matrices, specify everything except for those locations. And now what you see is that by simple evaluation of these functions, we can estimate the fooling rates in which the network misclassifies these images without having to do any sampling or augmentation or any of that. And you see this is perceptually aligned, in which this digit 9, this is a digit 1. And those expressions says that if you generate covariance matrices such that you corrupt those pixels that show in red, this will result into high fooling rate. Well, this is perceptually aligned because 1 would look like a 7 in these cases. And there are other examples where you have a 2 that might look like a 0 and so on. But even more nicer example is it wasn't really clear to us and to the community briefs for whether or not adversarial attacks can be sampled from Gaussian distribution. It seems such a Gaussian attacks to be very simple, much more simpler and trivial to be adversaries. And here's what we do. Is we say, okay, so let us try to optimize this function where we would like the network to misclassify an image M into thinking that it is actually incorrect class label J. The correct class label for this is I. And what we do is that we maximize the difference between the expected logit scores of the network. And if the difference here after optimization is positive, meaning that the average prediction of the incorrect class label is higher than the correct class label. And we optimize this for the input distribution itself. So what is this actually doing? Essentially, we're not designing a single adversary, but we're generating a full distribution in which once we sample from that distribution, on average, we'll make this 9 be predicted as a 2-pi network on an average prediction because we're mapping those expectations together. Or make this 9 look like a 3 or 4 or a 7 to the network and fool it in this way. And this says something that Gaussian noise, if optimized properly, can actually be targeted adversaries as well. Now we can do also non-targeted attacks in which you don't really care about to what class label you flip. What matters is that you flip it to incorrect label, but you can also do sparse attacks. So you don't really need to corrupt all pixels, but I want to corrupt alpha% of those pixels. So you can do the same thing where you minimize this in the hopes that if you get a negative quantity here for the objective function, meaning that there exists a maximum for this average prediction to be higher than all other, to be higher than the correct class label. You can do this even for large data sets, like on ImageNet, you optimize for these images for networks like AlexNet or like LDNet on MNest. Really, there are lots of other applications that there is no time for that to discuss it here, but this links to problems like network certification and verification through randomized smoothing. Because now, since you know the average behavior prediction of the network, you don't really need to do any augmentation. So first of all, you can get away from the need of, if you want to make the network robust against Gaussian noise, you no longer have to sample noise anymore because we know what's the average behavior of the network at the output subjected to this noise. So this replaces this data augmentation issues. We also have experiments show that it's actually strong against all other types of adversarial attacks. But also related to something that we can discuss later if someone is interested, it heavily relates to performing certification of networks, in which we say that the network is provably constant, having a constant prediction for all epsilon bolts around the inputs. And this can be used to train smooth classifier in this way. Right, so this takes me to the last part of this presentation, where we analyze, again, the same block of layers, but we'll look at decision boundaries specifically of that block through this lens of tropical geometry. But what is this tropical geometry? Well, it is the younger twin to algebraic geometry. In algebraic geometry, we're interested in finding the solution set to multivariate polynomials on this algebraically closed nice field, which is a complex field. Tropical geometry is exactly the same. We're interested in solution set to some polynomials, but over some semi-ring, where we refer to it usually for historical reasons as a tropical semi-ring. Now, just to remind you, a ring is a set of two binary operation, addition, multiplication. Semi-ring is just that the addition does not have to be invertible. So what is this tropical semi-ring? We'll define it as follows, or it is defined as follows, that the addition between two elements is the max between two elements, and the multiplication is the addition. And you see why it's a semi-ring, because the max is not invertible. And you can define tropical powers, which is the tropical multiplication, but multiplication is addition, therefore a to the n classically is n times a. So what is a polynomial, really? A polynomial is a sum of monomials, but now it is a tropical sum of monomials. So this is an example to my monomial. This is in two variables. And so I have tropical sum of three monomials, but that tropical sum is the max. So I have three terms, C and this and that term. But the x squared times y is tropical product, that's addition. So that's classically x squared plus y. And x tropically to the raised to the power 2 is simply 2 times x. So whenever I say tropical polynomial, think about a function that is a max over a set of hyperplanes where the slope of each of these hyperplanes is non-negative integer. It's a convex piecewise linear function. Now, this is an example. If I plot some of these tropical polynomials, you'll see that basically they are a set of linear functions, almost linear everywhere, except for some few locations whenever some two functions are equal to each other. So here x equals to y, y equals to 0, and x equals to 0, but you can construct other tropical polynomials. Right, so because we're interested in a solution set, we need to define what does it mean to say a tropical polynomial vanishes? And the right definition for this apparently is the set of location x's where I have the function f, which is my tropical polynomial, achieves its maximum at least twice in those monomials. Or if you will, the locations where the function is nonlinear. So in this example, this could be achieved its maximum at two monomials, x equals to y, or x equals to 0, or y equals to 0. So actually, tropical hypersurface is actually these curves that we're plotting here in red. And why is this the right definition? There's lots of literature on this, but apparently this is the right definition that helps us recover lots of classical results from like fundamental theorem of calculus, also results from algebraic geometry too. And so what we're going to do now is I'm going to construct something. Well, I'm not going to tell you why. We're going to construct something called dual subdivision to these tropical hypersurfaces. And to people doing complex geometry, this wouldn't be a very surprise to them because it relates a lot to problems like hyperplane arrangements or edge versus edge and vertex representations of polytopes. So let's say I have a divariate polynomial. So this x is actually a vector. What we're going to do is going to raise it to RD plus 1 by appending these exponents to the biases. And this is biased because it's a tropical product. So this is like addition classically. So I raise those AIs and CIs to RD plus 1. I'll take the convex hull of those and do orthonormal projection into RD back again. Whatever I get is my dual subdivision. I'll give you an example here. So if I have this 2D tropical polynomial as follows, I'll construct this in R3 and take the convex hull of those. So for example, in 2x, this is like x plus 2. And therefore, this is 1, 0, 2. If I take convex hull, I get that shape. Orthonormal projects like looking from top as a bird's eye view, and the dual subdivision looks something like this. So it's a complex polyhedron. But why? Why do you really want to construct such an object? It's because the dual subdivision is dual to the tropical hypersurface by how the name would suggest. In which, let's say I have this tropical polynomial given as follows, and the corresponding tropical hypersurface for this actually are these four red lines. Now, if I construct the dual subdivision of this and overlay it on top of this plot, it will look something like that, in which there is a one-to-one correspondence. So the duality comes into two different properties. The first property says that there is a one-to-one correspondence between each of these vertices, or perhaps nodes, of this duality are into one-to-one correspondence between every one of these cells where the functions are linear. And the other property says that actually those tropical hypersurfaces are normals to the edges of this dual subdivision. Great. But how is this useful? Well, Zhang et al. Very recently showed that any arbitrary deep network can be written as a tropical rational between two tropical polynomials, H and H. And remember, the division is the inverse of multiplication, but multiplication in tropical sense is addition. Therefore, classically, it's the difference between two tropical polynomials. While this may sound really surprising, how would possible that arbitrary deep network is ratio between two tropical polynomials? Well, actually, you can see this very simply by observing this result by Mills R, where any piecewise linear function, so if the network uses ReLUs or leaky ReLUs, for instance, therefore we can write it as a difference between two max functions over a set of hyperplanes. But I know that the max across set of hyperplanes is a tropical polynomial. This is classically difference of two tropical polynomials or ratio of two tropical polynomials. So how did Zhang et al. Use such a result? Where they said, okay, if I have an arbitrary deep network, and it can be presented as a tropical polynomial, let's say this is my tropical hypersurface, right? And where this tropical, as we mentioned before, in each one of these cells, the function is linear. Now, one way to measure the capacity and expressivity of neural networks is to count how many number of linear pieces do you have for that network. So what you can do instead of counting these cells regions, which could be very difficult, you can construct a dual subdivision instead and count the number of vertices on this polytope. So you convert this algebraic problem of these edges and the intersection between those and the hyperplane, the hypersurfaces, into a completely combinatoric geometric problem where counting vertices on polytope to say something about the expressivity of the network. But this relates to the first property, and what we're really interested in doing is taking use of this second property, which says that the tropical hypersurfaces are normals to these edges. So the result says the following, that if I have, again, the same block of letters, affine, ReLU, affine, we have this first result that says the decision boundaries for such a network, so I have a binary output networks, I have doing two classes, affine, ReLU, affine. The decision boundaries are a subset to a tropical hypersurface of some tropical polynomial that we can construct. So I know by Zhang et al. That each one of these functions can be written as tropical rational. So the decision boundaries are really nothing, are the locations x's where those two functions are equal. So if I rearrange this, I really am looking for decision boundaries, I'm looking for locations where this tropical polynomial, because it's a tropical product of tropical polynomials, it's a tropical polynomial itself, whenever this tropical polynomial is equal to yet another tropical polynomial. And what we're saying is that if we take the tropical sum of those two pieces and look at the tropical hypersurface of that, that thing is a superset to the decision boundary. But how is this even possible? Well, this is what the decision boundaries look like. I'm looking for locations where two tropical polynomials are equal, but this is equivalent to saying I want to look at the max of a set of hyperplanes are equal. And essentially then the decision boundaries are locations where A equals to C, B equals to D, and in those cases. Now what we're saying is that we'll take the tropical sum between those two pieces, and basically this is tropical sum is a max, but each one of those is tropical polynomial, then it is yet another max. So the max of maxes is the max of all arguments. And then I'm saying I want to look at tropical hypersurface of that, but the tropical hypersurface by definition is the locations where I have at least two monomials equal to each other. And therefore I can see with this construct, studying this tropical hypersurface will always be a superset to my decision boundaries. And now since we have that, you would ask, okay, then what is the dual subdivision to this tropical hypersurface? And this is given by the second result, which is very hard to parse from here, but essentially that dual subdivision stating that the dual subdivision is very well structured. It is the convex hull between two zonotopes, ZG1 and ZG2. And this is very nice because zonotopes have very nice properties, like they are centrically symmetric, they have parallel edges, and we can enumerate their vertices in polynomial time with respect to line segments. So great, and we have some results in how to enumerate them efficiently. So what's the big picture? Before we conclude, the big picture is that if I have a neural network, I have a decision boundaries for that network. What I can do is I can construct a dual subdivision to some tropical polynomial called R, in which the normals to the edges of this polytope, the dual subdivision, are superset to the decision boundaries. So those are the normals. I'll always find normals such that they are parallel to my decision boundaries, right? And not only that, but I can always go from a neural network to a dual subdivision and from dual subdivision to a neural network. And therefore we can ask now questions about how would we perhaps perturb this dual subdivision while maintaining its orientation to maintain the decision boundaries in order to get networks that have nice properties. And I'll just hover over some properties that we can use about this, for instance, pruning. So what you can do is say, okay, if I have an over-parameterized network that has this dual subdivision, what I can do is ask the question is it possible that there exist parameters in the network that corresponds to points in the interior of this convex hull? in which the convex hull will actually be preserved, and therefore the normals will be preserved, and thus the superset will be preserved, and therefore decision boundaries will be preserved. And by doing so, we can then go from this dual subdivision to the network, in which now we have constructed a smaller network with the same identical decision boundaries. Now, this is a computational problem, of course, so we solve it in an optimization fashion where we approximate a dual subdivision with another dual subdivision by approximating those zonotopes directly. But remember, we're optimizing over network parameters. This problem is not quadratic because those G's have all A and B, but you can run several solvers to solve this and enforce something like sparsity constraints on top of that. And you can do lots of experiments and show that you can actually do very well compared to other methods that do pruning directly, ignoring this idea of having decision boundaries in mind. But you can also validate all other methods that claim to preserve decision boundaries. So this one work called lottery ticket hypothesis, they claim that their method preserves decision boundaries in an iterative fashion. And what you can do now really, this is the decision boundary, and usually we get this by doing lots of full passes through a network, but we don't need to do that anymore. We can just construct the dual subdivision, and you see how those normals are actually parallel to the decision boundaries themselves. So if you run this lottery ticket, you would see that indeed the polytopes themselves are preserved in terms of orientation. So the decision boundaries actually don't change, reaffirming the claim of the authors. Of course, if we compare this to other methods, the decision boundaries per term much, which is a way to verify this without having to do these four passes and visualizing the decision boundaries. The last application that you could do with this is tropical adversarial attacks. So in adversarial attacks, we're really interested in moving this sample to the incorrect class. But you can look at a dual view to this, in which you say, instead of moving the sample to the incorrect class, let's perturb the network such that we move the right decision boundary, in which this point looks like as it was in C2 instead. So you can put down your classical adversarial type of objective, and you add to it this very nice term that essentially says, please minimize the perturbation in the dual subdivision. I want to have dual subdivisions that have little perturbation compared to the original subdivision. And what you see that is, this is my original network, and these are the decision boundaries. What you see in green is the dual subdivision to that. Now, if you run that algorithm and optimize it, you see that the point does not change location, but the decision boundary has moved up. But it's actually the right decision boundary that moved to the top, in which if you plot the dual subdivision to that, you'll get this dashed polytope. You see that the dashed and the green one are exactly identical, parallel on those edges, except for that right edge that we're optimizing for, in which you see the normal actually has moved up compared to the green one that points downwards in parallel to these points. So you can do, of course, experiments with, you show that also if you move different decision boundaries, the right edge of that dual subdivision will be perturbed. Of course, with that, you can construct also adversarial attacks too. So there are lots of extensions to this, perhaps beyond just a single layer neural network. This opens doors to several directions of free formulating classical problems, and we're interested in extending these mixed volume results to tropical geometry as well. So by this, I can end my presentation by talking a little bit about timeline achievement. So I started my PhD roughly in 2016. I presented 5 different works, and I was fortunate enough to do an internship with Intel Labs in Munich for 6 months with Radlin. And depending on this corona epidemic, I will either be working remotely for Philip Torr in Oxford as a postdoc until this situation is resolved, and then I can move there somewhere in the summer. I'd like to thank the committee members, Bernard, Wolfgang, Peter, and Yima, for dedicating time for this thesis. I know it takes lots of time. And also to the external collaborators and the amazing Chaos collaborators who have been with me in this journey. Those are only subset of the people, but at least the people have published work with. Special thanks to my parents who have been with me throughout this journey. Of course, not the journey of PhD only, but the journey of life, generally speaking. This work would not have been possible without them. I want to add one specific slide to Bernard. So I did something similar to Andrei Karpathy did. Essentially what I did is I looked up my email, and I've tried to look at how many emails that I received Bernard since I started my master's degree. And that averaged out almost roughly to 2 emails a day. And I want to pinpoint that somewhere through this process, and we switched completely to Slack, where I stopped receiving any emails from Bernard altogether because all the messages were over Slack. And despite that, there was like almost 2 emails a day I was receiving from him. So I want to, this tells a lot about Bernard's dedication, not to only me, but I'm sure with everyone there, this project would not have been remotely possible and not even close. And definitely taught me and many other researchers in the group to how to be independent researchers and carry out our own research. Also, the special thanks to the Ivo family. There are many people, unfortunately, have graduated. They don't have a picture with everyone, but this is at least the most recent one. And also special thanks to all my friends who are not affiliated with CAUS in any sense. And some of them are actually here in the chat and so on. So thank you all, and with that, I conclude my presentation.
All right, thank you, Adel. I didn't know that I was sending you so many emails. I guess if you added the Slacks there, that average would go up, that's for sure.
Yeah, definitely.
Yeah. All right, great. Thank you for the great talk. So now is the time for questions from the general audience. If you have a question, just please raise your hand and I can call on you, and then you can ask your question.
Sure. Can Silvio or Mu'tasim can watch out these raised hands, and they can unmute the person who wants to ask questions.
Okay. Yeah, sure. So who has a question? There should be at least one. Nobody. I guess everybody is still overwhelmed from all the content. So if there's no questions from the general audience, Victor has one. Victor, go ahead.
Yeah, can unmute.
We can hear you, sir, Victor. Now.
We can hear you.
Okay. Yeah, thanks, Adel. It's really impressive all the amount of work. Regarding the tropical geometry perspective, could you please remind me again, like you cannot extend it yet to like more than 2 layers because this is a combinatorial problem, so it's too expensive to compute the hyperplanes for the network, the convex hull.
Yeah. So Victor's question is, why did we stop at affine relu affine? Why can't we construct this dual subdivision of the decision boundaries for larger networks, like maybe 4 or 5 layers? The reason is you can still do it, and you can have formulas for that. But the problem is that you will lose all structure afterwards. So if affine relu affine gives you a structure that is convex hull between 2 zonotopes, if you add another affine in the relu layer, you will get the convex hull between 2 objects, where each one of these objects is a convex hull between 2 zonotopes. And once you do this, you almost lose all structure. And constructing such a thing will be combinatorically hard and expensive, deeming the process really
I see.
computationally invisible.
Yeah. Okay. Thanks. Yeah. I think that addressed my question. Thanks.
Sure.
Okay, great. Any other questions? Okay. I don't see anybody else. So maybe it's time that that the general audience please remove yourself from Zoom, leaving only the committee members. Okay, we'll wait a few seconds. There's a lot of people. We're down to 22 now, 21. I can speed up the process by throwing people out.
Maybe, I'm not sure. I think everyone speaks English. I don't think anyone doesn't, but I can say that. إذا بتقدروا حدا بس تطلعوا هلا تسيبوا الميتينج تعملوا تطلعوا من الغرفة.
I'm removing people.